Okay, so we're moving on to section 10.4. Now we're going to be adding and subtracting radical expressions, or just radicals, adding or subtracting radicals. And just like with, variables and expressions, right? You remember like terms? Well, we can only add or subtract like radicals, okay? And two radicals are like radicals if they have the same index and radicand, right? So for example, if I have, I should label this example 1, right? So suppose we have 3 times the square root of 5x and 7 times the square root of 5x. Okay. Are these like radicals? Well, what's the radicand is the thing that's inside the square root, the 5x. Are those the same? Yeah, 5x and 5x, they're the same. Right. What else has to be the same is the index. Remember what the index is? That's this number up here. For a square root, it's invisible. It's the 2. Right? But those are the same. So they have the same index and they have the same radicand. So these are like radicals. Okay. Which means, we can add them or subtract them. We'll do that later. Let's do another example. Suppose I have negative 6 times the cube root of 7 and negative 6 times the square root of 7. So these are almost the same thing, right? But remember, they have to have the same radicand. The 7 is the same, that's fine. But they also have to have the same index. So the index here is 3, but this is a square root, so the index is naturally a 2. But 2 and 3 are not the same, right? So these are not like radicals. These are unlike radicals. So these we cannot add or subtract, right? Okay. Let's say I have, 12 times the 4th root of 8y squared, and let's do negative 5 times the 4th root of 8y cubed. Okay. So notice that in this case, the index is the same. They're both 4s, right? So they're both 4th roots. But are the radicands the same? This is 8y squared and 8y cubed. Well, those are not the same, right? Because the exponents are not the same. Everything under the radical has to be exactly the same, right? So these are also not like radicals for that reason. Not like radicals, right? Yeah. So far only the first one were like radicals. Now notice in the first one, you might say, well, wait a minute, what about the 3 and the 7? Those are different. Yeah, they're different, but they're not underneath the radical. They're not, right? They're not radicands. They're not inside the square root sign, right? Well, remember, what are like terms, right? If I write, 4x squared and 3x squared, are those like terms? Right? In other words, can I add 4x squared plus 3x squared? Sure. Right? That's just 7x squared. Right? These are like terms. Even though the 4 and the 3 are not the same, they're the coefficients. They're the things in front, right? So yeah. But if I have, let's say, 4x cubed and 3x squared, now these are no longer like terms. Now we can't add them because the exponents are different, right? So that's kind of what we're doing here, but with radicals, right? Okay. So let's do another one. Example 4. How about the square root of 5 and the square root of 20? Are these like radicals? Right? Well, they're both square roots, right? So the indices, the index is the same for both. They're both 2, so that's good. But what's underneath? The 5 and the 20. These are not the same. Okay? So these are not like radicals. Okay? However, the story doesn't end here. Even though they're not like radicals as they're written, they actually can be like radicals. So what does that mean? Because look, 5 is not 20, right? 5 and 20 are not the same, so that's why I said they're not like radicals. However, what's 20? 20 is 4 times 5, right? So if I rewrite the square root of 20 as the square root of 4 times the square root of 5, notice that the square root of 4 is 2. So the square root of 20 is really just 2 times the square root of 5, right? We had to simplify that first. But after we simplify it, I have 1 times the square root of 5 and 2 times the square root of 5. So now these are like radicals. Because now the index is the same and the radicand, the 5 is the same in both. Right? So you see where this is going. If they're like radicals, I can take 1 square root of 5 plus 2 square root of 5, and when you add them, you get 3 square root of 5. Right? But you can only do that because they're like radicals. It's like adding 1x plus 2x. You get 3x, right? But originally, it looked more like, it looked like x plus y, right? So I might have, 3x plus 4y. These are not like terms, so these cannot be added. These cannot be simplified any further, right? So, yeah, so we can only add or subtract radicals if they're like radicals, right? And even though this here in example 4 was a tricky example, because the way they were written here, it did not look like they were like radicals, but that's because we didn't simplify it. After you simplify it, then they became like radicals, and then they can be added or subtracted, right? So yeah, you have to simplify everything first before you can declare, hey, they're not like radicals, okay? Okay, so now I think we can get to actually adding and subtracting. And in fact, we did one very quick example here, but let's make that a little bit more explicit. So I think we're up to example 5, yeah? Sorry, example 5. Sorry. All right, example 5. So let's add and simplify, which, it might remind you of chapter 7, right? Adding and subtracting fractions. So I'm hoping you find this a little bit easier than that. But right, so let's start with an easy one. Suppose we want to add and simplify 3 times the square root of 14 plus 5 times the square root of 14. Right? So you just have to check. Square root of 14, square root of 14, these are like radicals, right? So that means we can essentially just factor it out. We're doing 3 plus 5 times the square root of 14, which of course 3 plus 5 is 8. So this is just 8 times the square root of 14. Okay. Yeah, again, they're not all going to be that easy, but you got to make sure you know how to do the easy ones first, right? And the same thing, you can also subtract, right? So, example 6, so let's subtract and simplify. Simplify. Sorry for sloppiness here. Let's do 17 times the square root of 3x minus 13. Sorry, 13 times the square root of 3x. Well, again, the square root of 3x and the square root of 3x are the same, right? So these are like radicals. And because of that, we can just subtract, right, the 17 minus the 13, which is 4, right? 4 times the square root of 3x. Right? And let me remind you, this is no different than if you did, 17 times y minus 13 times y. You would immediately recognize this, I hope, as 4 times y, right? So you can just think about the y here as being this complicated expression, the square root of 3x, but that's just like the y here. Oops, y. Okay? But it's the same idea. Same idea. All right, let's do a slightly harder one, I think. Example 7. So we're going to go back to add and simplify. Let's do, the square root of 8 plus the square root of 18. So I can just hear some of you shouting, well, that's easy, that's 26, right? So that's the square root of 26. I hope not. Please don't do that. Please do not do that, right? I warned you earlier, get rid of all that. I did warn you earlier about this, so you might have forgotten, but I think in 10.1, I said that if you have the nth root of a plus the nth root of b, that is not the nth root of a plus b. Right. Nor is it true when you're subtracting. If you have the nth root of a minus the nth root of b, that is not the nth root of a minus b. So I wish it were that simple, right? I wish I could tell you that, yes, this is just the square root of 26, right? 8 plus 18 is 26. Unfortunately, that's the wrong answer. That's not going to work here, okay? So how do you get the right answer then? Well, remember, these are not like, these do not appear to be like radicals, do they? Right? Because they're both square roots, so that's a good start. But the 8 is not the same as 18, right? 8 does not equal 18. But remember, just as in this example, these did not look like they were the same either, and they're not, but when you simplify them, they ended up being like radicals. So maybe we can simplify these, right? So let's start with 8. We know 8 is just 4 times 2, so I can write this as the square root of 4 times the square root of 2. And the square root of 4 is just 2, so this is 2 square root of 2. What about 18? So 18 is, well, you can do 3 times 6, but it's easier if you do 9 times 2, because this is just the square root of 9 times the square root of 2. And the square root of 9 is 3 times the square root of 2, right? So, yeah, now you see it, right? Square root of 2 and square root of 2, these are like radicals. These are exactly the same. So this is no different than if you had, say, 2x plus 3x. You know by now that that's 5x, right? And so in this case, you're just doing, I didn't need to erase that, sorry, but I wanted to remove the clutter here, right? You know that this is just going to be 2 plus 3, right, times the square root of 2. In other words, 5 times the square root of 2. Right, and that's simplified. Okay, so I want to show you something just to show you that this in red over here is correct, that these are not equal. So hang on. Okay, so I just needed to remove a little clutter here. But I'm going to rewrite this. So again, this is the final answer. 5 square root of 2 is the correct answer here. But I want to unsimplify this, right? I'm going to write 5 as, well, the square root of 25, right? And the square root of 2 is already fine, right? But because it's a product, right, you are allowed to multiply them, 25 times 2, and we know 25 times 2 is 50. So this is really just the square root of 50. So remember earlier when I wanted to demonstrate that, a lot of you probably are thinking this, and you're not alone. I mean, look, I probably thought this too. I thought that this was the square root of 26, right? It just looks right. It looks like it's got to be, right? But as I showed you earlier, right, definitely not. It's not the square root of 26, okay? But here's what it is equal to. This is equal to the square root of 50. Now let that sink in for a second, because I know you're thinking that can't possibly be, right? So in your mind, you're probably just erasing the square root sign. You're thinking, wait a minute, 8 plus 18, how is that 50? Well, it's not. It's not. But that's not what this says, right? This says the square root of 8, right, plus the square root of 18 is equal to the square root of 50. And whether you believe it or not, this is correct. In fact, you can check this on your calculator, right? Calculate these, add them up, right? Add them up on your calculator and see what you get. Hang on a second. I got to do this on the calculator, right? So the square root of 8 plus the square root of 18. My calculator says that, hang on, this is 7.071067 blah, 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 right? 812, I think. Yep. Now, put in the square root of 50 on your calculator. Put in the square root of 50, and my calculator says that this is 7.0710678812. These, I think, are the same number. Let me make sure I have all the digits right. Yeah, these look exactly the same. So, right, so even though this looks funny here, these are in fact equal. And, right, why do I say it looks funny? Because, again, a lot of you are kind of ignoring the square root part. You're looking at 8 plus 18 and 50 and saying, well, that can't be right. But the point is you cannot ignore the square roots. They're there. They're part of the answer. Okay? Right. On the other hand, don't answer the square root of 50, because the reason is because that the square root of 50, right, this is not simplified. This is not simplified. So how do you simplify the square root of 50? Well, we did that way down here, right? You split it up, and then you write it as this answer here, 5 square root of 2. Right, so this is the same as the square root of 50, but, right, 5 square root of 2 is the simplified version. Right, so this is the correct answer, and it is also simplified. That was our goal, to add and simplify. Right, so yeah, don't answer square root of 50 because it's not simplified. Right. The correct answer is 5 square root of 2 down here. The one in the box, right? I always put a box around my final answer. It's a good habit. Okay, I think we can do another one. Let's maybe do a subtraction. So this is example 8 already. Well, example 8. So let's subtract and simplify. Simplify. Okay, yeah, let's do another square root. You're not going to see cube roots that much, but right, so let's make, sorry. All right, square root of 75 minus the square root of 12. So, right. Okay. And by now you must realize that, yep, you cannot just do 75 minus 12, right? That would be what, 63? So, yep, we can say definitively that this is not the square root of 63, right? We know that's wrong. Right? We know this is wrong. Okay, so yeah, so bad habit. Get that out of your head. Don't even think that anymore, okay? Because that's not how to do this. Okay, so how do we do it, right? Well, right, we have to simplify first, actually. 75, right, is, well, it's 25 times 3, right? So 25 times 3 is 75. And we can split this up as, right, the square root of 25 times the square root of 3. And the square root of 25 is just 5. Right? So the square root of 75 is really just 5 square root of 3. Okay. Simplified, right? This is the simplified version, right? Okay. Now just do the same thing with the square root of 12, right? What is 12? Well, you can think of it as 6 times 2, but these aren't perfect squares. These are not going to help, right? Instead, how about 4 times 3? Right? Because we know the square root of 4 is just 2. Right? So square root of 4 is 2, and then times the square root of 3. Okay? So see how that works? Now we have 5 square root of 3 minus 2 square root of 3. These are like radicals, right? We can subtract them. Just take 5 minus 2 times the square root of 3. That's just 3 square root of 3. Okay, so that's the answer here. 3 times the square root of 3. Right. Don't get confused. This 3 is not small, right? It's not the cube root of 3. Right? So don't make this 3 here in front. Don't make it too small because that'll look like a cube root, and that's not the same thing, right? Okay. And to unsimplify this, this is also square root of 9 times square root of 3, which is the square root of 9 times 3, which is 27. So remember when we said earlier that this is not the square root of 63, right? It is instead equal to the square root of 27, right? But again, 27, right? This is unsimplified. This is not simplified. So don't leave it like that, right? Leave it as 3 radical 3, 3 square root of 3. Okay, so I think I said I was going to do a cube root, and again, you're not going to see a lot of those, but I'll try to keep it simple here. So I think we're example 9 already. Yep. Oh. So this, okay. So this will be, yeah, let's keep it simple. The cube root of 16 minus the cube root of 2. Okay. Right, so we know it's not the cube root of 14. Yep, don't even go there. That's just not going to work. Okay. Instead, we have to simplify these. And 16, why is that not simplified? Well, because we can think of this as, well, you might be thinking 4 times 4, right? After all, the square root of 16 is 4. But these have exponents of 2's, and in fact, if you write it that way, it looks like this is simplified. Yep, 2 to the 2, 2 to the 2, and 2 is less than 3. But that's the wrong way to think of it. This is a cube root, right? Remember, the cube root of 8 is 2. Right? So we want to split this up as the cube root of 8 times the cube root of 2. Now, what about the cube root of 2? Well, the cube root of 2, 2 to the 1, that's simplified, right? 1 is less than 3, so there's nothing we can do with that. Okay. On the other hand, the cube root of 8 in the first term here is just 2. So this is 2 times the cube root of 2 minus, and it might help to put the invisible 1 here, 1 times the cube root of 2. Right? So this is just 2 minus 1, right? 2 minus 1. Times the cube root of 2, which is just 1 cube root of 2, and we don't need the 1 in front, right? So all of this is just the cube root of 2. Right? Okay? Does that seem okay? Again, if you're thinking, wait a minute, 16 minus 2 is 14. How do you get 2? Again, that's the bad habit, right? You're thinking that you can just get rid of the cube roots here, and you can't, right? It is true that, right, 16 minus 2 is 14, But it is not true that the cube root of 16 minus the cube root of 2 is the cube root of 14. Definitely wrong, right? In fact, we know what it is. It's the cube root of 2. So yeah, so that's correct. In fact, you can check that on your calculator, but you know, it happens to be correct here. Okay, they're not all going to be this easy here, because up until now these are just numbers, right? And you're going to see variables too. You're going to see x's, right? X's and y's. So yeah. So I'm gonna clear all this and then start fresh, and we'll do some more examples. Okay. So still in section 10.4, and this is example 10, I guess. So we did a lot of examples, but I did remember to keep count this time. So add and simplify the square root of 125x to the 5 plus 2x squared square root of 5x. Okay. So yeah, this is a more typical problem. When you have variables, it's always a little more complicated, but we'll go through it step by step, and you'll see this one is actually not that bad, right? It involves simplifying, right? Simplifying this expression here, right? The square root of 125 times x to the 5th. Well, right, you can split it up. You can do the square root of 125 times the square root of x to the 5. Right? Now, what do we do with this? Well, let's worry about that later, right? In fact, some of you may notice that this is already simplified. There's really nothing else to do here. So we'll come back to that later. Let's worry about the first term only here. We'll come back to this later. Right. Okay. Yeah, I didn't need to do that. All right, so 125, right? What's 125? Well, it's 5 times 25. And you can split this up again, 5 times 5 times 5. So this is 5 cubed, but this is not a cube root, right? There's no cube here. This is a square root, right? So this is a 2 here. So really, we want the square root of 5 times the square root of 25. Just want that, right? And likewise, with the square root of x to the 5th, we can think of that as the square root of x squared times the square root of x squared. That gives us 4 x's, and now we need one more for x to the 5. So square root of 25 is just 5. Square root of 5 is, well, whatever it is, square root of 5, right? And then the square root of x squared is just x. That's also x, and then we have square root of x. Right? Again, I've been ignoring the second term here. Excuse me. Okay, so now what? Well, now we just bring all the x's in front, right? X times x is just x squared, so we get 5x squared. And then in the back, we have the square root of 5 times x. See that? Right. Now let's go back to, right, so I think we're done here. There's nothing else to simplify, right? So now we can go back to the second term here. And how do we simplify this, right? So the 2x squared is outside the radical, so that's good. What do we do with the square root of 5x? Well, we could split them up, but, right, the exponents are 1s, and 1 is less than 2, and so they're simplified. So just combine them again and leave it as 2x squared, right, times the square root of 5x. And notice that the square root of 5x in the first term matches the square root of 5x in the second term. Now they didn't originally, right? We had 125x to the 5, which looked nothing like this, right? But now they kind of look alike. These are like radicals, right? And in fact, the x squared also has to be the same. X squared and x squared, those are like radicals. The only thing different is the 5 and the 2. So those are what you add, 5 plus 2, right? 5 plus 2 is 7. So you have, right, think of 5 of these plus 2 of these. Oops, I didn't mean to cross it out. 5 of these boxes plus 2 of these boxes is 7 boxes, right? 7 x squared square root of 5x, right? That's this box here, right? So you have 7 of them. And that's it. So that's our final answer. right? So all of this, when you simplify it, you just get 7x squared, oops, times the square root of 5x. Okay. I hope that helps, and yeah, let's do another. We have time to do another one, I think. So scroll down. Yeah, so this will be example, I think 11. Yep. All right, so example 11. So how about if we subtract? We haven't done a subtraction one yet. Subtract and simplify. So I'm going to think about this. How about so this will be 6 times the square root of 20 y to the 7 minus 2y cubed times the square root of 45y. Okay, I think this should work. I hope this works out. So how do we subtract these? Well, first of all, right, these don't look anything alike. These are not like radicals as they're written, but hopefully when we simplify them, they will be. So that's the idea, simplify. Let's start with the first term over here. Okay, so the 6 is outside. We can leave that alone. But the square root of 20, right? And then the square root of y to the 7. Right? So we'll leave the 6 alone. But 20 is 4 times 5, right? So this is the square root of 4 times the square root of 5. Right? It's a 5. And the square root of 4 is 2. So this is 6 times 2 times the square root of 5. Right? Right. Oh, and 6 times 2 is 12. So that's going to be 12 square root of 5. Right. What about the, so I noticed I ignored the square root of y to the 7. So how do we take care of that? Well, remember, there's two ways. You can split this up as the square root of y squared, square root of y squared, square root of y squared, square root of y, or you can write it as y to the 7 divided by 2, because 7 divided by 2 is, well, 3.5, so 3 plus a half. Make that 3 a little bit bigger. Yeah, so 3 plus a half, right? And remember, when you add the exponents, you're just multiplying y to the 3 times y to the 1/2. So we now have y to the 3, and then y to the 1/2, that's just the square root of y, right? The index is 2 here, right? Okay, now we're almost done. We just put the y cubed in front, right? So this is 12y cubed, and then times the square root of 5y. You can combine them all at once, right? See how that works? So I think we're done, at least with the first term, right? That's just the first term. Now we got to do it all over again with the second term. We have to simplify all this now, right? Yeah, so the 2y cubed, that stays in front. That's as simple as it gets. But we also have the square root of 45, right, times the square root of y. In other words, we can split these up, right? So yeah, this will now be square root of 45 times the square root of y. And the square root of y is already simplified, so it's just the 45, right? So what's 45? Well, you could do 3 times 15, but there's no perfect squares here, right? 15 is 3 times 5, and there you go. 3 times 3 is 9. So this is 9 times 5. Right, so leave the first 2y cubed in front, and then split this up as the square root of 9 times the square root of 5 times the square root of y. Okay, so still have 2y cubed, and then the square root of 9 is 3, right? That was the point of writing this as the 3 times 3 as a perfect square, right? However, the square root of 5 is not a perfect square, so we have to leave that alone. and then the square root of y. So notice we have negative 2 times 3, that's just negative 6. We still have y cubed, and then we have the square root of 5 times the square root of y, or combining them again, square root of 5y. And I think that's as simple as it gets, right? So that's the second term. Let me just write it again, minus 6y cubed times the square root of 5y. So now you just have to notice that all of this matches all of this. Right? Y cubed, square root of 5y, square root of 5y. So we can subtract those two boxes, right? 12 boxes minus 6 boxes is, well, 6 boxes, right? So what's in the box? Y cubed, square root of 5y. Okay. And so we're done, right? Again, where did I get this 6 from? 12 minus 6, right? It's no different than, 12a minus 6a would be 6a. Right? Yeah, there's no a in this problem. The a is what's in this box here, the y cubed square root of 5y. Right? So that's the idea. Right? So, right. So again, I don't think it's going to get much more complicated than this. This is about as hard as it gets. So, go through it again if you have to, because this is a good example. It's one that's going to come up over and over. And I think I'll do one more with a cube root. Again, not that you're going to see a cube root very often, but, if it happens to come up, then, it's good to know how to do. On the other hand, I wouldn't expect that, say, on a test. You might see it in the homework, right? So if it's in the, I guess you might see it on a test, but I would call it unlikely. But let's just say, just in case, let's do one more. Let's do a cube root problem, and then hopefully move on from there. Okay, so we want to add and simplify, well, these expressions here. I guess I should read them off to you, right? So cube root of 135 x to the 7 y squared plus 4x times the cube root of 5x to the 4 y squared plus 3x squared times the cube root of 5x y squared. Yeah, so here we're adding 3 terms, right? So it's a little bit harder because it's a cube root, and we have 1, 2, 3 terms. Okay. So in order to add them, we have to simplify first, because as they are written, these do not look like radicals, right? The only thing I think we can say that's the same about all of them is this y squared, right? Y squared, y squared, y squared. That's the only thing that matches, at least for now, right? So yeah, we've got a lot of work to do. Let's start with the first one, right? The 135. So how can we split up the 135? So if you take 135, right, and divide by 5, oh, hang on, 135 divided by 5, keep getting the wrong answer. Yep, 27. And that's a perfect cube, if you remember, right? So, yep, 27 times 5, right? Yeah. Well, okay, and then we still have the y to the 7. Sorry, x to the. Sorry, I'm getting kind of confused, right? X to the 7 y squared, right? I was going to split all these up, but let's do that on the next step, right? So let's do the cube root of 27 times the cube root of 5 times the cube root of x to the 7, and then times the cube root of y squared. And then we're going to take these second and third terms. We'll do those later. Right? Let's just do this first one for now. All right, cube root of 27, you should know that that's 3. Right? Cube root of 5, well, you should know that that's simplified, right? Because the exponent is 1 and 1 is less than 3. So, okay. What about the cube root of x to the 7? So we're going to get x cubed times x cubed. Well, okay, let's do it the fractional way. Let's do 7 over 3. Right, what's 7 divided by 3? So I'm going to copy these over again. So 7 divided by 3 is 2 with a remainder of 1. Right? So 2 plus 1/3. Or better yet, x to the 2 times x to the 1/3. Right? And for that matter, we could write this as y to the 2/3, but right, 2/3 is already less than 1. It's already simplified, right? 2 is less than 3, so we didn't have to do that. We could leave it as the cube root of y squared, right? And in fact, this x to the 1/3 will be written as the cube root, make the 3 a little bigger, the cube root of x. Okay, so I think now we have just about everything we need. We have the 3 in front. Oh, I forgot the x squared. That goes in here. Sorry about that. Actually, that should come in front now, right? So 3x squared in front. And then what's under the cube root? We have a 5, an x, right? The x squared is in front, not underneath the radical, right? And then the y squared. So look, I tell you that we're done, but not even close, because we have to do these other terms up here. All we did was the first term, so we simplified the first term, the first expression, and we're done with that. Now we go on to the second expression, right? Luckily, I think this will be a little easier, in particular because the 4x is already outside, and then we have the cube root of 5. Notice that's the cube root of 5, same as here. And then we have the cube root of x to the 4, and then the cube root of y to the 2. Oops. Cube root of 5, right? Now, what's wrong with the cube root of x to the 4? 4 is not less than 3, so we pull 1 out, right? This is going to be, I'll do it the quick way here, the cube root of x cubed times the cube root of x to the 1, because 3 plus 1 is 4, right? Y squared here, right? So we have 4x in front. We have the cube root of 5. And then the cube root of x cubed is just x, right? The 3's cancel. And then the cube root of x, we don't need the 1. And then the cube root of y squared. So we have x times x, that's x squared. And then we have, what's under the cube root? Well, the 5. And the x, and the y squared. So just to show you that this is exactly right, the same thing we have here, but the 4 and the 3 are different, right? So again, these two things are going to be like terms, like radicals. And what do we do with this last term? This last term, well, we could split this up, but the problem is that all the exponents are already less than the index. So this is already simplified. Let's just bring it all the way in front here, downstairs, and y squared. Bring it down a little bit. And now you should be able to see, after I erased all these circles here, little smudges, sorry about that. Yeah, you should be able to see that all 3 of these are actually like radicals. So let me show you that. We have x squared in front, and then underneath the radical we have 5xy squared. Again, we have the x squared in front, and then 5xy squared under the cube root, and then x squared, and then underneath the cube root, 5xy squared. So they're all identical. The only thing that's different are the coefficients, right? 3 plus 4 plus 3. Well, 3 plus 4 is 7. 7 plus 3 is 10. So that's 10. We still have the x squared. And then we still have the cube root of 5xy squared. So finally, we are done. That should be our final answer to the original problem up here. which was, like I say, what made this more difficult was the fact that there were 3 terms, although to be fair, the last one was already simplified. We didn't have to do anything with this. But we did have to simplify the first 2 terms. And what made it a little trickier was the fact that it's a cube root instead of a square root, right? So, yeah, so because of that, this was, I would say, I'd say a more difficult problem. But like I say, one that you're probably not going to see, but I can't rule it out. So it might help to go through this one again. And I think there's probably at least one of these in the homework where you do have a cube root. But like I said, I really wouldn't worry too much. I wouldn't spend a lot of time on these. I would spend more time on, say, number 10, which should have been a little bit easier, and maybe number 11. So they're all good problems, this one being the hardest, most complicated. But I hope that helps a little. And like I said, I realize how frustrating this is. And, I can't tell you how much I miss teaching, miss being in front of a class, because, I really need your questions, and not having questions to answer in real time is a little bit frustrating. But like I say, you can always send me an email, and I will answer your questions by email. And in fact, if you have a really good question, either on Connect Math or from the homework set, feel free to ask me, and I'll by request, I will do an example in one of these videos. So please ask me questions. Continue to ask questions by email. So I hope that helps.